Hello, welcome back. Let's go ahead and get started on section 4.4. So particularly today, we're looking at this definition of linear combination, and we're looking at spans. So we have seen linear combinations before in the context of real vectors. Now we're just going to think about them in general vector spaces. Because again, general vector spaces are just taking the context of real numbers and allowing us to abstract it a little bit. Alright, so let's go ahead and take a look at this picture I have here. So I'm going to label these vectors. So let's say this bottom blue one we'll call V. And then let's have this red one be our U1. And the black one sticking out the back will have be our U2. Alright, so let's see here. U2. Okay, so our question is it possible to get to V by going along U1 and then going along U2? Some amount. Alright, so in fact, yes, V is a linear combination of U1 and U2. And how can we verify this? Well, let's just think about this in terms of the geometry. U2 is going to allow us to jump off of this red vector, and it allows us to jump at a particular angle. So let's get that angle correct. Select and move this. So, in particular, if we follow this angle out, so this would be some amount of U2, it's slightly longer than U2 is, and then we go up U1 a small amount. Right. So in fact, we should be able to get to every single vector in 2D space using just this U1 and U2 that we have here. So one note I will say is that I do know the actual number. So if V is the 3, 1, V is equal to 5 over 12 U1. So this U1 we have right here is 5 twelfths times the length of regular U1. And then we go backwards 4/3 U2. So it's longer and going the opposite direction, which we did see. Okay, so again, between these two vectors, we could get to every single vector in two-dimensional space. So what we're going to say is that the span of these two vectors was equal to R2. So from our example, the span of our two vectors, U1 and U2, was all of two-dimensional space. So let's think about all of the possibilities we have in 2D. So in R2, if we have some vectors, okay, we have three options. Either we could get all of R2, all right, and we probably need at least two vectors to get the span, and we need these two vectors. They couldn't have been on the same line, so U1 cannot equal a multiple of U2. Alright, and vice versa. Alright, what else could we have gotten? Well, if we just had one vector or they both were on the same line, we have a line. Right? So, for example, the span, if we just took U1 up here is everything that's along the line that is U1. Let's do that in pink. Right? So U1 is the vector 4, 4. So everything that's on that line is x comma y, where x equals y. Alright, right? Because this is the y equals x line. So y equals x line. Alright. And then lastly, the final option is that we could just have the origin. So that's the span of just the 0 vector. Right? Notice that this line in the previous example also had to contain the origin. Okay, so those are 3 options in R2. Right? These might appear, we might have like more vectors in these, like a U3 here, or we could have the 0 vector appearing multiple times, we could have the 0 vector in here, or more vectors, etc. But if all 3 of these vectors are on the same line, then we know that our span is only going to be a lot. Alright, so next I want to consider 3-dimensional space, what spans could look like. Well, we could get all of 3-dimensional space, and before I write it down, just think about how many vectors do we need to put in there in order to span all of 3-dimensional space. Well, we need at least 3 vectors, and they each have to have 3 coordinates. They all have to be vectors in R3. Right? And we need at least 3 of them, and none of those 3 can lie on the same plane. Well, every 2 will define a plane, and the third has to not be on that plane. Right. And then we could just get a plane if, say, we had 3 vectors that were all on the same plane. It has to contain the origin. And if we have 2 vectors, we're going to get this. So this is the span of U1 and U2, as long as they're not multiples of each other. This works a lot like R2. If these were multiples of each other, what would we get? Well, we'd just get a line. So let's draw Let's draw our line. Has to pass through the origin, and that's the span of a single vector, or any number of scalar multiples of that vector added in. And then lastly, we could also get the span of just the 0 vector being just the origin. Alright, so this is what spans look like in real vector spaces. You either get the whole space, or 1 dimension smaller, or 1 dimension smaller, or the point. So, on the other hand, we could have, let's take a look at other vector spaces, which are totally possible. Alright, so let's take a look. What is the span of 3 plus x, 2x minus x squared in the polynomial vector space of up to 2 dimensions? Well, in some sense, this is just the set of scale the first polynomial and scale the second polynomial and add those 2 things together, such that C1 and C2 are real numbers. Right. Now this to me isn't the most meaningful description, so one thing we could do is rearrange it so that we have like the constant terms and then the x terms, so we have a C1 plus 2C2 x, and then the x squared terms. So I think that looks a lot more like a polynomial to me. It kind of makes a little more sense. You could go one step further and sort of think about, okay, we have 2 unknowns, and this middle one has a relationship to the other 2. So how might we write that? Well, we could write, this is a plus bx plus cx squared, that's a generic polynomial, such that b, well, what's the relationship between b, the x coefficient, and the constant term in the x squared coefficient? Well, it's 1/3 times the constant term plus 2, from the 2 there, times the negative of the term in front of x squared, where a, b, and c are real numbers. All right. So whichever one of these has the most meaning to you, then that's the one that matters, right? Excellent. So that is what I wanted to say about linear combinations of spans and spans. Let me know if you have questions. Have a good one. Bye-bye.